So, so we are here in the last class. I think we all understand what we meant by this thing. A laser beam is attenuated to operate at a very low power, 1 nanowatt, so that we can. The intention is that whether we can actually isolate a energy quanta or photon in space or in time. And we found that if it is 1 nanowatt, so if we place a photodetector in the path of the beam and we capture the count for 1 nanosecond duration, then roughly around 8 photons will be counted. So photon counter will show 8 photons. Another 1 nanosecond, you will see another round about 8. It can happen that maybe one time it is 8, another time 9, and another time 7, and so on. On an average, you're supposed to get 8 photons. Now, question is that if your gating time, this 1 nanosecond, is reduced to 1 by 8, whether you will be getting only 1 photon or not. That's the question. So that means if you see 30 centimeter long beam, you will get 8 photons. So if it is a very good source, I suppose to get that these 8 photons should be at an equal interval. But practically, because of the various reasons from the source side, vacuum fluctuations, noise, so a lot of things will be there. Because of that, you may not get they are at a regular interval, but on an average, we can assume that there are 8. Okay, but practical situation is not like that. Sometimes what happens, even if it is just 1 time 8, 1 time 9, that would be fine. On an average, you should supposed to get almost if you chop properly, you can detect a single photon. But thing is that the laser source shows this type of distribution. This is called Poissonian distribution. You see this one, Poissonian is written here. And where instead of 8, we just assumed a round figure, maybe some 10. Okay, 10 photons on an average you're supposed to get. But if you keep on sampling this 10 photon duration time again and again, you get a very nice distribution. That is the distribution. This type of distribution is called, mathematically you can express as a Poissonian distribution. So what does it mean? So you see this x-axis is written as P omega n. Omega stands for photon frequency or energy, h bar omega, and number of photons. So each time if you sample a certain length or certain duration of time, then most of the time you will be getting probability of getting say 10 photon here. This is the number of photons, 10 photon, the probability will be maximum, say about 0.12 or so probability. But some probability will be there to get lower than 10 photons, and some probability will be getting there higher than 10 photons also. So it can go up to 20 photons, even more. Sometimes you can get in the same length maybe 20 photons clubbing together. And sometimes you can see also there is a some length, you will find maybe no photons are there also. 0 or 1, 2 photons will be there for the entire length. That is the property you will be getting because of various reasons. We will be discussing that. That is called actually Poissonian distribution. And this type of distribution you get from a good so-called, we know that, laser source, which is normally when we call a laser, what does it mean? Laser light normally monochromatic and coherent, and it has a good direction, it has a particular polarization, everything is there. But in practice, you will see that number of photon distributions will be like that. That means there will be some kind of photon emission rate may not be constant all the time. Okay. Suppose instead of 1 nanowatt, if you are scaling up, then your average photon number will be increasing, but this distribution will remain same. So here average number will be, you can say more, instead of 10, this scale will be changed, but the profile will not be changed. Okay. And this is actually somewhat better distribution compared to your normal incoherent light sources, like thermal sources. Like if you just consider like a black body radiation type source, there actually you will be getting the highest probability is that you are not getting anything. Highest probability will be not at all any photons. So number of photons will be increasing. This solid curve, if you see solid rectangles, this is actually more or less we can define for a black body radiation. Even LED, normal bulb, whatever, if you see, that their distribution will be like this. So you sample equal time for detecting the photons, then the distribution will be like this. So that is actually called thermal light. Now question is that whether you can actually engineer this distribution. So the best source known to us is laser, that gives this one. You can engineer the source such that you can get something narrower distribution. Okay, here another example given where maybe a laser light is light source or your photon source is a little bit intense enough so that you can get average is 100. Okay, on an average you should get 100 for a certain duration of time or certain length of the beam. But most of the time you will be getting 100 or around 100. The standard deviation will be lower than whatever you are supposed to get from the Poissonian. So in that case, if it is narrower, I think there is a high chance that if you want to single out a single photon, that is possible, because you know that every time 100 photons will be there, or 99 or 98, something like that. So you can actually chop perfectly so that the quantum particle of electromagnetic wave, you can actually, there is a chance you can single out. And that type of source is called sub-Poissonian source. So laser light, normally this is Poissonian and this is called sub-Poissonian. Okay. And like a little bit of incoherent, so not really laser, maybe LED, super luminescence LED, SLED called. That type of source, if you have, they are actually, their distribution will be, standard deviation will be more than that of your Poissonian one. And that will be called super Poissonian. So for quantum photonic application, you should try to get sharp Poissonian source where you can actually really quantum state of a photon can be preserved and you can actually manipulate, you can single out, isolate, and you can use them for certain applications. So here is just a distribution function shown here. For example, the thermal distribution, this type of distribution, whatever it is shown here, that is actually derived by Bose-Einstein. Bose actually derived, and it was actually sent to Einstein, because initially when he tried to publish, it was not possible. Then he wrote to Einstein, and then also to convey to understand all the Einstein's work, etc. Both have to learn German language, etc. That there are stories are there. I think I'm not going into that details. But then Einstein recognized that that's a good insight is there, and together they published, and this is the result. So what is this distribution says? Suppose if you want to get probability, this n means probability of getting n photons for a certain duration of time or certain length of the beam is 1 over this one, where n bar is the average one. Suppose if your average photon number you supposed to receive, maybe say 100, you put down here 100, here you put down 100, here also it will be 100, and then this is the power n, whatever value comes here multiplied by this one, that will be the probability of obtaining n photons. Okay, probability means this probability you are getting. So if you just plot, you will be getting similar, this type of plot here. So it can be average 10, it can be average 20, you can just simple MATLAB program you can try, and you will be getting this thing. And Poissonian distribution, that is laser, this is also, it has a expression. We will try to derive this one in our class, that how this thing comes, because it's like some statistics is there, probability distribution you have to consider, and then you can find you can start from the normal distribution function like a Boltzmann distribution, and then apply the photon or boson property, and then you can get this thing. Now question, how to obtain sub-Poissonian? Okay, so this is the thing, how to obtain sub-Poissonian light, that is one thing. And once next thing is that once you get a sub-Poissonian or some kind of when you are getting sub-Poissonian light of source, sometimes it is called in a different name called squeezed source, and that squeezed source normally we can understand from the quantum mechanical fluctuation point of view, and a little bit of classical concept is needed. Okay, so to understand that, to understand properly this quantum property of the photons and its applications, manipulations, I have taken this classical instrument because this classical instrument, some important device is used in this classical instrument is the beam splitter. Okay, so and this beam splitter, you know, it is actually the main building block for any quantum photonic device. If you want to devise a quantum photonics device, and if you want to completely ignore the use of beam splitter, then you are gone. Because beam splitter actually helps to understand the quantum property of a photon. Not only quantum property of the photon, you can get quantum interference also, so-called quantum interference. What is that quantum interference? How that will be achieved, how you can get quantum interference means you want to get some kind of superposition state, quantum mechanical superposition state. Earlier you learned that. So before that, we wanted to know a little bit of classical aspects of this instrument and classical aspects of the beam splitter also. Because many things, the quantum property of any photonics device, quantum transfer function, I would say, of the photonics device, that can be directly devised from the concept of classical behavior, classical theory. Here, that is the one aspects to explain or to discuss this particular instrument called Michelson interferometer. I think some of you might have heard about Michelson interferometer. This is one of the sophisticated equipment and used maybe I think about 200 years ago by Michelson for different type of measurement, particularly astronomy and some kind of sensing measurement. Okay, and here while using this, we will be also able to learn the one special aspect of the source, light source, and that is called temporal coherence. So this temporal coherence I am discussing here because in quantum photonics, normally this temporal coherence is not that important. There is another type of coherence will be used that I will come to that point. But to understand that, it is better to understand what is temporal coherence also. So I am just trying to explain the background of this instrument so that we can step by step go towards your quantum photonics characteristics. Okay, and so what is this? Try to understand this one. I will be just, I think if you just look at it, maybe you will be understanding, but I will also ask a couple of questions just to know that whether you are aware about all this. If you are knowing all this, then I can go very fast. Otherwise, we have to go a little slow. You see, you have an input light coming in. Classical light you just assume for the moment. Classical electromagnetic wave coming here. Okay. And this is a beam splitter. And this beam splitter is designed or in such a fashion that 50% will be reflected and 50% will be transmitted. It is normally glass plate you can use, half silver mirror, silver coated, and it is coated such that 50% can go in the forward direction and 50% can go this direction. And then that means your incoming beam is split into two parts. And then this one part, after traveling certain distance, L1, you have a mirror here. And then what happens? This mirror is 100% reflecting, you assume. So whatever you are using here, all the instrument, all the device, beam splitter to mirror, let us assume they are lossless. Nothing is lost. So if it is 1 milliwatt comes here, beam splitter, classically you can say that 0.5 milliwatt will go this direction and 0.5 milliwatt will go this direction. And mirror, after hitting mirror, exactly 0.5 milliwatt will return back. And here another path it is going L2, and after coming back it will be again 0.5 milliwatt. Then what is happening? When it is coming back from this, it is passing here directly. Again, you see beam splitter, it will go according to its property 50%, and here it will be coming 50%. And whatever going this direction, you can ignore input side for the moment. Okay, so it is going this direction and coming back is this way, and going and this way it is coming. Right? Now, you see, this is your output, and you are putting here a photo detector, right? Now I have written equation 225. Just see, I have written E out. I'm not, I am just writing first what is the amplitude, electric field, what electric field you will be getting here. Total electric field. You must know that if I just only consider 0.5 milliwatt coming here and 0.5 milliwatt going, sorry, 1 milliwatt coming and 0.5 going this direction, 0.5 going this direction, and after coming here, how much power will be there? So if you calculate according to the intensity and try to find out what is the value, then you will be doing mistake. Can anyone tell why? If I ask someone, yeah,
Sir, yeah, sir, can I?
yeah, go ahead.
Yeah, so the intensity would, like when we're taking the field, we take it as a complex quantity, we take it as a phasor.
Uh,
And when we take intensity, we usually take the mod square. So we lose out on the phase information when we
yes.
try to add.
So normally, whenever you are dealing with two beam of electromagnetic wave, because it has a phase, it is a field, and that is a vector, right? So that phase inform, if I just try to see the intensity, what phase it is coming here, you don't know, and what phase it is coming here, you don't know. Ultimately, since it's a vector, you have to see first the vector addition, and then you can try to find out what is the total strength, squaring it, total field. So normally, this type of device, it is a linear device, so you have to see linear superposition of individual components, right? So phase information needed, that's why we start with the amplitude, field strength. So suppose at your photodetector, you have one component E1, another component E2, right? And then you see, I am writing here 1 by 2 and 1 by 2. And this E input is nothing but amplitude corresponding to input power. Whatever power is coming, corresponding E input is there. And K is the propagation vector, you know. And here also L1, L2 is there, and I have added delta. Now I want you to identify whether the expression is correct or not first, and identify the different phase components where from coming. So this is the L1 written means, you can imagine then whatever going L1 path and returning back L1 path. So after beam splitter, I am not considering any length here. So that means this is going, coming back L1. And when we are multiplying K, what you get normally? E to the power KL. What you get normally? E to the power JKL. What is that? Anyone? Whom to ask? Let me see. Gantashala. Ramakrishna?
Yes, sir.
Yeah. Can you explain what is this?
Yes, it is a propagation vector, sir, e power jk dot r.
Say it again.
It's a propagation vector, sir, e to the power of jk dot r square.
So what
It's like that.
you call it normally? KL1, JKL1, K times L. What you call normally?
Yes, sir.
No, I'm saying that K is the propagation constant. If you
Yes,
multiply
sir.
propagation constant with the length, path length, what you get?
Phase, sir.
Phase, correct. So you get the round trip phase, right? 2 times.
Yes, sir.
Yeah. Can
Yes,
you
sir.
unmute? You have a lot of noise
Yes,
probably.
sir.
Mute. So that means you are getting the phase, round trip phase after going here, whatever phase accumulation happening to in whatever the things here, whatever beam is going here. But I am writing here EIN, you remember that is coming here. Is this half meaningful here? Where from this half coming? Anyone can explain? Uh, Sasank wants to explain.
It's a 50-50 beam splitter. So half of that will go in one direction, the other half will go in the other.
Haha. So when we call 50-50 beam splitter, is that 50-50 amplitude splitter?
No, it's supposed to be 50-50 intensity, I think.
So then why half I am writing there?
Uh,
So for amplitude, what would be the splitting?
it should be 1 by root 2, 1 by root 2.
It should be 1 by root 2. So I have written 1 by 2. Is that correct?
No, I think it should be 1 by root 2.
It should be 1 by root 2. Anyone can tell that 1 by root 2 or 1 by 2?
Sir, it should be 1 by 2 because there'll be 2 times splitting.
Exactly. Because you see, first time it is going 1 by root 2 and another time it is coming back again 1 by root 2 you will get amplitude. And 1 by root 2 will go this direction. Is not it? So this is the amplitude. You see, that is actually amplitude. In fact, it is 1 by root 2 by 1 by root 2 multiplied by that is 1 by 2. Similarly, the other beam also. Other beam also I have written L2. Can anyone explain why I am putting extra delta? I will ask whom? Animesh, you tell me. Where from this additional delta is there?
Sir, it is in perpendicular direction.
Perpendicular direction means?
The two beams.
That's why delta. So delta means if I consider this KL2 times 2, that is the phase because of the path. This KL1 because of the path.
So the
So
two
then-
beams are out of phase actually, means by delta.
Who is saying that?
So Shovik.
Shovik. So two beam out of phase. Where from that out of phase is coming?
Means when the beams are getting splitted, one beam is getting out of phase by that delta. Extra phase is getting in.
Where? What is the source of that extra phase?
Sir, perpendicular direction will change to parallel direction.
Why?
Sir, is it
So because
path difference between the beam?
Path difference is that is what exact path length you are putting already. KL1, KL1 and KL2. But I am putting additional delta.
The beam splitter adds a phase to one of the, so the reflected one gets an extra phase versus the transmitted one.
Who is saying that?
Shashank.
Shashank.
Yes.
Yes, I think that's the correct answer because the phase, it can be different between reflected beam and transmitted beam in the beam splitter. But if you see, the first beam, if you see, that is going one reflection and then coming back, transmission. And the second beam, also going one transmission and reflection also. The identical, na? Both are going through one reflection, one transmission. What is the problem?
So when the first split happens, the reflection is happening on the second surface.
Yes.
So it's like you're taking from a
So,
higher refractive to lower refractive.
I think that is very important that in the beam splitter, and that also helps later on to understand the beam splitter, how it is actually conserving energy. When we consider a lossless beam splitter, energy conservation only possible if whenever it is reflecting from the top surface, that is actually you are reflecting from the air to this surface, right? Air to glass. And then when it is transmitting here, this one, that time actually the glass to air is coming here. So in that case, two types of medium will be observed. So there are certain property we will find that there will be some kind of phase difference will be there. Normally we will see that is pi phase difference will be there in round trip. Okay, we will be understanding, because ultimately this type of beam splitter will be using in case of integrated photonic circuit. So where we will be using waveguide beam splitter. So there also similar type of beam splitter property will be using, and that time details will be clearer. So that means we have, because they are sourced from same input, their phase will be different because of the beam splitter. And also if there is any phase is actually created in M1 and M2, if they are not identical, slightly different, that also we can add here delta. That is why it is done. And then I think Animesh was saying that this in plane and perpendicular, whatever the things are there. In this equation, I have ignored a very important point actually. Can anyone identify that?
Sir, it is a plane polarized light.
Yes. Suppose suppose these two beams, what type of polarization you have to consider? If it is so-called TE or TM or whatever the things, we consider that this polarization is preserved. Whatever going, you know that normally when it is coming T to TM, the boundary condition will be different. All those type of things can happen also. But here we are considering they are identical. All the polarization are same. That's why I have not put anything here. They are sourced from same light source. So that's why we are considering their identical polarization. In the output also same polarization you will be getting. So if they are same polarization, then their total superposition will, you can see that polarization means direction of electric field. If direction of electric field is different, then total electric field to find, you have to take your vector summation. So in this case, I'm just simple summation I'm considering, assuming that both the components have same polarization. And anything else I am missing? Anyone? What is the equation of a plane wave, by the way? I will be asking to Emmanuel. Emmanuel, are you there?
Yes, sir. K dot T should be 0.
What?
K dot T should be 0.
A dot?
K dot T should be 0. That propagation vector dotted with electric field.
Propulsion vector dot. That is.
And also, electric field can be represented as a amplitude times e raised to I k dot r minus omega t.
Omega t part.
Yeah.
I'm just asking that omega t part. Normally, plane wave is that e to the power j omega t minus k dot r, right? So why I am not using omega t here?
So we are considering the interference at same time.
At the same time we are considering, because it is actually all the both the beams we are just measuring at the same time, so that e to the power j omega t we could keep on writing, but ultimately that has no meaning. Okay, that is the reason we are omitting here. Okay, now next line. So it is understandable that two beams, how it is coming, 1 by root 2 y 1 by 2 and what delta. Delta you can just ignore also for the things, but I have put here so that you should not forget that beam splitter can introduce some phase. Right. So I have taken factor of half E input e to the power j2kl1 in 226, and then this one, and then simple your algebra. Right? You are getting E out square and then 2E input square cos square, and K, instead of K I am writing omega yc delta L and delta plus delta. K I have represented as omega yc. Now Normally it is an interferometer. Do you see any interference here? Do you see interference fringe in this case? If you have a screen at the output, will you see any interference fringe here? I will be asking Neil Aswin.
Sir, I'm not sure actually. Maybe not.
Maybe not. Why you are not? Why you are doubtful? You have an expression in front of you. Now you have a photo detector, right? And you have a beam. Here we have shown only one line. Normally one ray is impractical. We have a beam, right? So suppose 10 micrometer beam size or 1 millimeter beam size or whatever. Now that 1 millimeter beam size is plane wave, right? And collimated, uniform. And that 1 millimeter beam is split it into two. And then coming back to your output. And entire 1 millimeter beam is falling in your screen. So within that 1 millimeter, will you see any interference or not?
Sir, I don't think we'll see because whatever is happening to one ray will happen to all the rays. So there won't be anything different.
So you will see the uniform intensity, right?
Yes.
Then why we are calling it as an interferometer? Anjana?
Sir, I'm not sure about it. As in, depending on the path difference between the two paths, uh, this and depending on that, constructive indifference and destructive indifference could happen.
Only
So
that is if you just change the delta L. If delta L equal to 0, what is the intensity you will be getting? Delta L 0 means, suppose this small delta you consider 0, for example, or constant, whatever things. So that ignore for the moment. If delta L is here, that means it is L1 minus L2 by 2, right? 2 times it is there, 2 delta L was there. 2 delta L is the L1 because L1 minus, sorry, delta L is equal to L1 minus L2. 2 times because 2 times a round trip. So you see, if it is delta L equal to 0, then the small delta also 0. Then your intensity is how much?
it will be maximum, sir.
A maximum. Why 2 times coming?
From each beam, is it something like that?
No, it's your input is EIN, right? Your input field is EIN. So does it mean that energy conservation is lost? Maximum, that is fine if delta L equal to 0. Any idea? This is this is a very fundamental thing you have to tell.
Yes, sir. Like the light, we have interference. Some like we get dark spot and bright spot. Here also we'll get a maximum intensity, and somewhere we'll get no intensity at all.
So that means you will be getting fringe.
Yes.
But I think someone explained nicely that there should not be any interference because entire beam plane, what is happening to one point, other point also happening same. So as a spatial distribution, you should not get anything.
So otherwise energy conservation will be lost.
Yeah, that's the problem. So how to, I am just trying to coming out of this paradox. Can you help? So this is the thing is, you have to see that after interference, this interference happening with the delta L, two beams going together, right? In line. So what is happening? When delta L equal to 0, their energy is doubled. But it can happen that this phase part is pi by 2. At a certain length, you will get phase part is pi by 2 also in the path itself. So it is propagating. So at certain point, energy is doubled, and certain point, as it propagates, it's like a standing wave type things happening, right? So some region it is a high energy and some region low energy, and that is propagating. That means your fringe is a traveling fringe. You are also getting a fringe, but that is a traveling fringe. Is that correct? That way you can explain?
So you're saying that it's like a temporal interference pattern, is it, sir?
Yeah. Is that correct or not? I'm asking. Can you just think of that? Okay, if delta L equal to 0, you are getting maxima, and delta L equal to pi by 2 omega c, whatever, omega c multiplied by delta L pi by 2, then it can be minimum. So that way it is happening.
Sir, in terms of standing wave, we can express
It
this.
is obviously it is not a standing wave, right? Both are traveling in the same direction. Okay, this is I'm not explaining this now. So normally Michelson interferometer, any textbook, everything, if you see, nowhere it is explained properly, right? But you have to find out. You have to understand this thing. I just keep you, but because this type of thinking is needed also for certain understanding. So I just leave with you, and next class I will be clarifying. And in the meantime, you just think. You can just study Google or whatever you can do, and try to get the answer. What is happening at any instant of time? Because you see, normally as it traveling, you have to see the average energy, right? So in that point of view, you just think about that, or whether you check whether this expression is whatever it is derived, it is wrong or right. So one thing is clear that you, depending on the delta L, you see the interference fringe, right? Normally, whenever you see the interference fringe, that is actually static. Time variation, you don't observe, right? All the time, same intensity will be getting. If you are just creating an interference pattern, all the time you will be, even though it is a high frequency oscillations are there, but you don't see that. It is always bright, dark you will be getting. So in this case, what is happening, you have to understand. So one thing is that I'm just a little bit going without disclosing that, just delta L equal to 0, and as a function of delta L, you can see that you can get high low intensity pattern, right? Interference fringe you will be observing, right? So that is normally what is happening. Suppose this type of instrument, what for it is, if you one of the path, if you have some certain kind of suppose you want to sense a particular sample, what is the refractive index, you place one of the path of this interferometer and see what is the intensity, and then you remove that one and you see the intensity, and comparing that you can find out what is the refractive index. some kind of sensing instrumentation purpose, you can utilize this type of equipment, Michelson interferometer. Okay.
Sir, we going to like change the path length
No,
to see the maximum intensity?
That is for sure. That expression is saying that if you change the path length, your intensity will be changing. But my point is that if at any point where you are getting maximum, right, that point you are getting highest energy, and that is double energy at that particular instant. I am just monitoring a particular point, right? And delta L equal to omega c by delta, whatever delta L you put 0, for example. It's a balanced one. So in that case, I am getting 2 times of input intensity, right? And I know that the entire screen intensity is same. So multiplied by area, you will get power. That means power is also doubled. But it is sure that if you just, that particular point, the intensity, I am just giving you a clue, that particular point for a given delta L, the intensity all the time you will be getting same. It is not that it is a traveling intensity, traveling intensity and bright and dark is traveling. In that case, you will see your detector will show you the average energy, right? At particular point, if you place detector, whatever that dark, bright comes, normally even if your electromagnetic wave is there, you see electric field maxima, minima is there, no? But your detector cannot resolve that type of frequency, that type of time resolution. It cannot show the maxima, minima amplitude, right? So it will just give you power, continuous power it will see, because that type of frequency, high frequency, that is 200 terahertz, that frequency cannot be resolved. I think.
Is it because so intensity is power per unit area, and when we have the input beam, it splits. So it splits into half the area in one track and the half the area in the other, and then when it comes back and interferes, the interfered the output beam would also be the same area as the two separate.
Yeah, that is same area.
Yeah, so if it splits into from A to A by 2 and A by 2, then the output beam would have an area of A by 2, but the energy has to be the same. So the overall intensity would be 2 times En.
No. Your input side, you have a power. If it is power is E by E input,
right?
Field strength.
En square.
And then when it is coming to a beam splitter, it's a amplitude splitting is happening, right? And when amplitude splitting is happening, preserving energy, of course.
Right.
So one side it is going E by root 2, another is going also E by root 2. That is amplitude. So when you add them together and then square it, then you will be getting again input square.
Yes, sir,
input square.
I'm saying that the width of the beam would be halved when they're splitting.
No. That cannot be. It's a beam splitter, no. Width of the, that means diameter of the beam will be reduced. You mean to say? No.
That won't happen. Yeah.
That won't happen. That is normally won't happen. So it is actually very trivial thinking. Just you think. Normally we don't think that this thing. We think that interference pattern means just in a screen I will see dark and bright. But here also you have interference pattern. But at a particular point, it is double energy is showing. Okay. And that double energy is it's a static there. All the time you will be getting that one. Delta L for a given delta L, all the time you will be getting same energy. So this is a simple question. You just think over. We will come back to that. Sometimes you should think also. Only I should not give lectures always. Okay. Now you see one thing is we should go a little ahead. Let us believe that that delta L will be that whatever energy you will be getting double, and then delta L changing, you will be getting energy less, 0, because it is a cosine function, cos square, right? So you have this frequency omega. Now I understand that as you the M1 and M2, suppose I keep M1 fixed, M2 I increase. That means delta L I am increasing very large distance. In that case, that maxima minima ratio will change or not? I'm saying that if the mirror separation, that L1 and L2, L1 minus L2 is very large, and then I am just slightly changing delta L, so maxima to minima will change or not? Maxima to minima ratio, that means contrast. From this expression,
So you're saying that for large delta L, if we change...
No, I am saying that you have a delta L fixed now, right? A certain length is there.
Right.
Now I am slightly changing delta L value.
Okay.
So it will be following cos square function. And after for a certain increment, you will get 0, right? Maxima to minima it will go.
Right.
Now, if this delta L is very large, big at the beginning, and then again you are trying to do same experiment, will you see any difference?
The contrast, I mean, from this expression, it seems like it wouldn't change, but I think it would drop because of...
No, as long as your omega is fixed, that is going to be the same, because expression is giving like that, right? What else? I think this expression, we have not compromised anything.
But what about like diffraction effects and all of that?
No, diffraction is not there here.
Okay, if we're avoiding that.
We have not used any diffraction principle here. Nothing is diffracted. No pinhole, nothing is there. No sharpage, nothing is there. No diffraction. Where from diffraction comes here? There is no.
I mean, for this expression, we have not considered, but like I thought, like in a realistic scenario, if we look at
diffraction means you mean to say that divergence or something like that you were.
Yeah.
Right. Okay, that is not there. That is not considered. Yeah.
Then
collimated beam.
Yeah, then it should be the same.
Yeah. So it should be same. L can be infinity. This delta L can be infinity. Right? And this type of source, that is called actually ideal source. Right? Ideal source because we have only one frequency, omega. That's called super coherent source, super monochromatic source, I would say. Perfect monochromatic light. That is the reason you get that delta L you don't need to bother about. But practically what happens, this monochromatic light source is practically difficult. First point I mentioned. I hope you are okay if I just continue another 15 minutes, right? 15-20 minutes I need to explain this slide a bit. If you just read this slide, sometimes in the textbook is there, but I need some kind of discussion so that everything will be clear. So laser light is considered to be nearly monochromatic, emitting light with a spread of delta omega around a peak angular frequency omega. Angular frequency you can consider that is omega equal to 2 pi f. Normally, if you see a laser light, you don't get a perfect line. There is a line width is there. Do you know, I think if you have studied a bit about laser, can anyone tell that where is the source of this bandwidth? Why? Because you know, normally laser is kind of stimulated emission. When we say that stimulated emission, that means one photon comes and that stimulate to emit another photon of same frequency, same polarization, same direction. That is a quantum mechanical phenomena. That I think time dependent Schrodinger equation, if you just solve, you're supposed to get that. But tactical laser, if you see, it does not happen. You have a line width normally. If it is emitting 1550 nanometer, you get some line width around 1550 nanometer. If it is frequency, say 195 terahertz, you will get bandwidth around that. Can anyone tell why this happens in any laser source? Anyone of you studied any laser course? Be frank. I suppose that Anjana, you must have.
Yes, sir. It is because of that energy time uncertainty that
Energy
we
times.
have this delta omega.
Yeah, energy side. Actually, there are many reasons. Many reason is that you see inside there are called homogeneous broadening, inhomogeneous broadening. If it is a gas laser, then
Collision
gas,
broadening, sir.
that means
Droplet shift.
Doppler shifts. So collision, all those type of things happens. Molecular collision, all these happens. And for solid state case, normally again this vacuum fluctuation, whatever you are saying, that uncertainty, vacuum fluctuation, that also contributes. Okay, so it is the practical thing we have to accept. Some bandwidth is there around peak resonance. Then if that is the case, now I come back to the source. Instead of omega, if it is delta omega, so you have some range of omegas there. What would be the consequence in this expression? Do you see something different? I'm not going to ask you what is the source of delta omega, but you have to accept that delta omega is there. Now in this expression, what you can expect?
So there'll be a distribution of k's.
There will be a distribution of k, correct?
Because of that, there will be some randomized phases that will
not randomized.
I mean, like it'll be with respect to the distribution.
Different frequency component will have different phase.
Yeah.
So you can get one frequency component coming in constructive interference there, but another frequency component, that point, it may be destructive interference. That means omega 1, if I just put down here omega 1 within that range, multiplied by delta L, it gives you, say, suppose 2 pi into integer, or pi into integer, and then pi by 2, that means odd multiple of pi by 2. It can happen also for some frequencies. So in that case, what happens? Overall contrast, it will be compromised. So maxima to minima, you may not get perfect. If it is a perfect omega, perfect 1 visibility and perfect 0 darkness will come as you change your delta L. But if it is omega is having some range, you may get a DC level all the time. And it can happen that delta omega, if it is very broad, you can imagine that you may not get also at all any contrast. Because if your thousands of frequency components are there, for example, broad, one or another, it will have some destructive, another maybe 50% will be destructive and another 50% giving you constructive, or some sequence it will be coming. It's a things. So you may not get also the interference pattern at all. If delta omega is very large, you will not get interference pattern. That means it's meaning that high low you may not get. And when you are not getting that, you are saying that that is actually completely gone. That is not at all a coherent source. So the delta, smaller the delta omega, the source is more coherent, we will call. Right? So we need some kind of quantification to characterize the source. And that is actually we consider as a temporal coherence. So the fringe contrast reduces with path length difference L delta L because of the existence of your delta omega L. And difference in time of flight, that means time of flight difference means this L2 minus L1 minus L2 round trip travel time instead of path length, you can just multiply with velocity and this time, then you can get this L. So that is actually called temporal coherence. That is actually quantified as a temporal coherence. So temporal coherence of light beam is quantified by its coherence time tau c corresponding to the path length difference L is equal to c tau c. So this is defined such that the interference contrast will be visible significantly when L, if you set your L, here this L I am just defining like this expression, delta L, right? 2 times delta L, that L. If it is less than or equal to LC. So you can tolerate up to certain path length difference so that you get your some kind of visibility of interference you will be observing. And beyond that, it will be whitewashed. Even if you change your path length, you won't see any difference. So from L equal to 0 to certain length up to LC, you can see the contrast is changing. Some visibility will be there. And beyond that, the visibility will be maybe there, but it is not measurable. You can quantify that, the visibility. Up to this visibility, I can define your this coherence time or coherence length. So you need that one. So how to quantify that? So this is an important formula because we will be using another similar formula for actual quantums to characterize actual quantum state of a photon. But here I am not considering anything photon, everything classical. But whenever we are considering similar type of expression, we will be using, but we'll discuss that later. And this is called actually, we define as a G1 tau. How it is defined, you see this one. Okay, so the temporal coherence of light beam can be quantified more accurately by the first order correlation function. This is sometimes called first order correlation function and or G superscript 1. This one has some significance, I will explain, and it is a function of tau. This tau means, that means corresponding to C L equal to C tau. That means how much time of flight difference is there between two paths. That is the tau. And that is expressed like this. What actually is this actually? You can imagine, you are taking electric field complex conjugate, you are taking at time instant t. And you are taking electric field after a delay of tau. And then you are just taking some kind of overlap. Okay. And that, because tau you are keeping a fixed, and then you average that over time. as your time pass. This tau is a fixed value. That depends on your path length difference, right? Now you just take average. For that tau, you take an average of this one. You measure it, that actually electric field you cannot measure directly, right? But you can mathematically express electric field at time instant t, and then you have a tau value is there, and take overlap and take average expectation value you are taking. That is expectation value you are expressing like this. This t must be very large, larger than at least many times larger than your at least your time period of your source. You have a fixed tau, and then you are integrating over a time up to t and taking average. That is what this one. Is that going to change if you are changing tau? If it is going to change, why? Anyone can explain? I have instead of L, I am just representing here as a tau, L difference. Now I have a fixed tau. Now I forget about whatever I explained earlier. Now you just only look into this expression. You have a field at t and you record it in your computer. Now you have another field that is coming in different path though, but you can consider without this instrument, you sample field after tau. Because you know that one path is coming earlier, another path is coming a little later, right? So instead of that same beam, you sample at a particular time instant, what is the amplitude, record in your computer, and wait after tau time lapse. When it is elapsed, you take another measurement of the field, and then you take overlap. Will that be all the time same? Suppose every tau I am measuring, every tau I am sampling and measuring, will I be getting same? We won't get, because whenever you are multiplying this, you know, at time, because this delta omega, whatever coming, that is because of the vacuum field fluctuation, and that vacuum field fluctuation causes some kind of phase fluctuation. So that means whatever phase was reaching to you at t, after certain time tau, the phase can be different, and that can be stochastic depending on the how much this delta omega spread is there. So if I just assume that two path and tau time, I am just capturing them with a delay. One beam is coming, another beam is coming with a delay. But the delayed one already originated little while earlier. That I am just trying to measure there, that point. So if their phase is not, it's fluctuating, that is going to be changed, right? So I just quantify that one. I just put, suppose I put tau equal to 0, what I will get? That means path length equal to 0. What would be the value of this one? If tau equal to 0?
1, sir.
1.
1, sir.
So that is actually that is the perfect coherence. That means your delta L equal to 0 basically. Now if you are just increasing your tau, because the phase all the time from the source whatever coming, I'm just talking not because of the path, source whatever emitted at t equal to some value and t plus tau value, they are not originating with the same phase. That means somehow they are incoherent. So if as I keep on increasing this tau value, this value is going to be dropped. Okay, so I can actually measure, I can say that this is a function, right? As a tau dependent function. So looking into the profile of this g tau, I can actually some characteristics I will be getting. From that characteristics, I can decide, okay, I put this tau, this distance, then I will be getting this much contrast. So this measurement, this characteristics is very important. And that thing you can find out if you know actually delta omega. Delta omega is measurable. In a spectrum analyzer you can find of a source, right? If you know delta omega, then you can find what is the function of this will be looking like. That I will be discussing in the next class. Okay, I stop here now. You just keep on thinking my other question. That is actually almost answer, but you think a bit.